Hey guys, welcome back to another lecture video for Chem 115. In this video, we are going to learn how to sketch a titration curve by calculating the pH of the solution as we incrementally add titrant into it. And so this video discusses the calculation for a strong base to a strong acid. So the base will be our titrant, and our acid, our strong acid, is going to be our analyte. Okay. And so if you guys recall, the titrant is what's inside the burette. And the analyte is what's going to be inside this Erlenmeyer flask. All right, so let's go ahead and get started. So in our hypothetical scenario, we have a 50 milliliter sample of a 0.100 molar hydrochloric acid, and that's titrated with 0.200 molar sodium hydroxide. And so before we start, I mentioned in the introduction that we're going to have a strong base as our titrant, and we're titrating it to our analyte, which is a strong acid. Now, on an exam, you guys are not going to have these clues to help you determine which set of calculations you guys are going to perform. And so if you guys are just given a word problem like this, you need to be able to determine what's the titrant and what's the analyte. And so there's some key clues that can lead you to that direction. So for example, the word sample. So the sample typically talks about the substance that's inside the Erlenmeyer flask. Okay, so typically the sample is inside the Erlenmeyer flask, and so therefore that's going to be our analyte. Okay. And so in this case, the analyte or the sample is referring to the hydrochloric acid. So hydrochloric acid will be our analyte. And once we figured out the analyte, then the other substance is going to be the titrant. Okay? And we need to identify what's the analyte and titrant so that we can visualize what's happening in each step of the calculation. All right. And so let's go ahead and look at what we have to do. So we're going to determine the pH of the solution when a specific volume of titrant is added to the analyte. And then we are going to take all of those values and we're going to sketch a titration curve. And so what we're going to do in this video is go through the calculations on how to determine the pH of the solution. And we're going to use the results of A, B, C, and D to finally sketch the titration curve for a strong base to strong acid. All right, so let's go ahead and get started. I'm going to go ahead and just highlight or take this portion of the question. I'm going to copy it. I'm going to just place it here. So the first item that we need to calculate is the initial pH of the analyte. And I always like to start by drawing my pictures. So I have my burette and I have my Erlenmeyer flask. And so I need to label the components, the volume, the concentration that's inside my burette and my Erlenmeyer flask. So here it says I have a 50 milliliter sample of this concentration of hydrochloric acid. Okay. So I already know the concentration of my analyte, and that's 0.100 molar HCl. And I already know my volume, which is going to be 50.0 milliliters. Okay. So this is not a titration problem because we already know the concentration of our analyte. And so if I scroll up, here I have the concentration of the sodium hydroxide, which is our titrant. So I'm just going to go ahead and place 0.200 molar of sodium hydroxide. Okay. And so this is our base, and this is our acid. And so now that we have all of the components labeled in this diagram, let's go ahead and address the question. And so what we're going to do is we're going to calculate the initial pH of the solution of the analyte. And so when we calculate the initial pH of the analyte, are we placing any volume, any amount of sodium hydroxide from the burette into the Erlenmeyer flask? And if you answered no, then you guys are absolutely correct. And so when you guys are calculating the pH of the initial pH, you guys are simply determining the current pH of this solution as it stands right now with no addition of the titrant. Okay. So no titrant is added. And so I'm going to go ahead and call this VB. So V is volume, and B is representative of the base. Okay, so the base, and that's B. And so VB is going to be equal to 0 milliliters. Or if you want to add in some sig figs, and I should be more precise, let's just say 0.0 milliliters. Okay. All right. Well, to determine the pH of my analyte, all I have to do is think about the reaction that's occurring inside this solution. I'm going to take away that arrow real quick so it's less confusing. So I'm going to go ahead and think about what's happening in this solution. Well, we have hydrochloric acid that's placed in water. And when that's placed in water, what will it produce? It's going to produce H plus and Cl minus. And so to calculate the pH of the solution, what we need to figure out is the equilibrium concentration of the hydrogen ion. And if you guys recall from earlier the topics that we covered earlier in this chapter, to calculate the equilibrium concentration of hydrogen ion, we need our value for X, which comes from your mass action expression, which is coming from your ICE table and the balanced chemical equation. Okay. So everything that we've learned in prior discussions of acid-base equilibria, we're going to apply to building our titration curve. Okay. And so so here we have our balanced chemical equation. We have hydrochloric acid that's ionizing to produce H plus and Cl minus. And so to determine the equilibrium concentration of H plus, which we see here, we need to build an ICE table. And so I'm going to go ahead and describe the initial concentration, which is 0.100 molar. And then let's talk about my change. And so hydrochloric acid, is that a strong acid or is that a weak acid? And so hydrochloric acid is a strong acid. And what do we know about the change for strong acids? It's 100% dissociation or ionization. And so that means that all of the hydrochloric acid that was placed in the solution is going to ionize to produce the products. And so we're going to fully consume all of hydrochloric acid. All of hydrochloric acid is going to break down. So at equilibrium, we have none left. And that is a feature or a characteristic of strong acids. And so what we have remaining is just 0.100 molar of hydrogen ion and 0.100 molar of our chloride ion at equilibrium. And in the problem, we didn't really have an initial concentration of product. And so keep in mind, we need to focus on what we're trying to solve for. We're trying to solve for the pH of the solution. Well, I already have the equilibrium concentration of hydrogen ion. And so therefore, if I just take the pH or the negative log of the concentration of H plus and plug that equilibrium concentration inside, I'll get the pH when I did not add any titrant into my analyte. So in other words, my initial pH. And so I'm going to take the negative log of 0.100. And so therefore my pH is going to equal to 1.000. Okay. And so when I didn't add any titrant into my analyte, it looks like the pH of the solution just by itself is 1.00. And so this is telling me that my analyte is acidic, which makes sense, right? Because hydrochloric acid is an acid, so it should make our pH very acidic. Now I'm going to go ahead and put these 2 points together, VB and pH. Because remember, at the very end, I'm going to build a titration curve. So I want to describe how much volume we added to the resulting pH of the solution. Okay, so that's 1 point in our titration curve. All right, so let's go ahead and look at the next problem. All right. So we're going to calculate the pH of the analyte after 10 milliliters of titrant is added. Now, when you're doing these types of calculations, you guys definitely do not. So it's you guys are going to work within that question. So even though these are like successive additions in real life, when you guys are working, when you guys are doing these problems by hand, you guys are just going to use the values that the problem is currently giving you. All right, so we still have the same scenario. We have 50 milliliters of 0.100 molar hydrochloric acid and 0.200 molar of sodium hydroxide. That's our base. And so let's go ahead and determine the pH of the solution after 10 milliliters of titrant is added. Okay. And so this time we're going to add 10 . 0.0 milliliters of sodium hydroxide. Okay. Now, remember that sodium hydroxide is a base, and hydrochloric acid is an acid. And so for part B, you're mixing an acid with a base. So that lets you know that there's a reaction that's occurring. And so we have to describe this reaction by writing the correct chemical equation. And so here we have HCl, hydrochloric acid, reacting with sodium hydroxide. And when this reaction occurs, what you're going to get is H2O and our salt, which is sodium chloride. Okay. So water is going to be liquid in state, everything else is aqueous. And so if you guys are writing this acid-base equation in terms of like a net ionic equation, then you're just going to go ahead and drop the sodium chloride, the sodium and the chloride from this chemical equation. Okay. And you guys don't have to do this. You guys can work with the equation that I have right now, but just for clarity, we know that the quote-unquote main reaction is going to just involve the hydrogen and the hydroxide. And so that sodium, that chloride, becomes a spectator ion so that we get the proton reacting with the base producing water. Okay. And by writing the net ionic equation, we can go ahead and describe the reaction just a little bit more clear. We can present it just a little bit more clear. Okay. Now, remember, what we're trying to do is calculate the pH. And to do that, we need to determine the equilibrium concentration of hydrogen ion. Well, once again, since we need to calculate the equilibrium concentration, that should invite us to think of the ice table. And so we're going to summarize the course of this chemical reaction through the ice table, where we're going to describe the initial amount of protons and hydroxides, and we're going to determine the change, and then finally we're going to determine the equilibrium amounts after the reaction has finished or has reached equilibrium. Now, very similar to the buffer videos that you guys hopefully have watched, when a reaction, an acid-base reaction is occurring, you want to describe the change in amount through moles, not molarity. You can do it through molarity, but that means you have to recalculate the new concentration when you add both of those volumes together. And so that's just an extra layer of calculations that I don't really want to personally, I don't want to work with. And so if you guys can just work on a mole-to-mole basis when you're describing a change in amount because a reaction is occurring, and if you can keep that thought in the back of your head and be able to recognize it in an exam problem type setting, then that overcomes that first hurdle of what to do or how to solve this problem. Okay. And so once again, I'm going to put it here. Since a reaction is occurring, okay, you want to convert everything into moles. Okay. You want to compare everything on a mole-to-mole basis. And this is a theme that you guys are going to see throughout this chapter, throughout this last leg of the chapter. And so for hydrogen ion, I have the concentration and I have the volume. And so I'm going to take this volume and multiply it by the concentration, but I need to convert milliliters into liters first. And so if I do that, I'm moving the decimal place 3 times to the left. So that's going to be 0.0500. Let's see here. 1, 2, 3. Yeah. 1, 2. Okay. So this is going to be liters times this by the concentration. And I'm going to go ahead and expand that concentration unit in terms of moles and liter. And so I have 0.100 moles of hydrochloric acid for every 1 liter of it. Okay. Volumes are going to cancel. And if you multiply both of these values, what we get is 0.1 times 0.05, 5.00 times 10 to the negative 3 moles of HCl. And so since this is the initial volume and the initial concentration, then this represents initial moles. And so I'm going to go ahead and put that 5.00 times 10 to the negative 3 moles to represent my acid, my strong acid. Okay. Oops. Now for my OH minus, the concentration is 0.200 molar, and the volume is dictated by how much I transferred into the Erlenmeyer flask. And so very similar to what I did with the acid, I'm going to go ahead and take the 10 milliliters, convert into liters. So that's going to be 0.0100 liters. So I'm going to convert milliliters to liters. And then I'm going to multiply it by its concentration. And so the concentration is 0.200 moles of OH over 1 liter. Okay. And I want you guys to notice that I'm kind of, well, let me just be consistent here. So I'll just go ahead and write NaOH. Okay. And so if I multiply these two, so 0.01 times this by 0.2, I'm going to get 2.00 times 10 to the negative 3 moles of sodium hydroxide. Okay. And so if you guys are looking at the identity of the substance, if I have this amount of sodium hydroxide, then that also represents the moles of hydroxide. Remember that sodium and chloride are spectator ions. Okay. So that's why when I'm putting it into this equation, I'm simply representing OH as NaOH and HCl as H+. So this is going to be 2.00 times 10 to the negative 3 moles. All right, and so remember that this is an acid-base reaction. And so if this is like the initial amounts, so this is like a war, I don't know, some Game of Thrones type of thing, right? This is the number of soldiers that we initially have. And when they clash in the battlefield, it kind of just makes sense by numbers, which one is going to lose and which one is going to win. And so 2.00 times 10 to the negative 3 is smaller then 5.00 times 10 to the negative 3. So it looks like after this reaction has occurred, all of the hydroxide will be consumed. And it will take down that many moles of hydrogen as ions. And at equilibrium, we'll have no hydroxide left. And yes, we are going to produce water. So we're going to add 2.00 times 10 to the negative 3 moles. And if you bring down the sodium chloride, we also produce that same amount. But remember what we're asking here. We're trying to determine what the pH of the solution is. And so water will not get us the pH of the solution. Sodium chloride will not get us the pH of the solution. The only thing that will give us this pH of the solution is the concentration of the hydrogen ion or the concentration of the hydroxide ion. And since there is no more hydroxide ion present, then it would have to be the concentration of H plus that will determine the pH of the solution. And if you add downward, this is going to give you 3.00 times 10 to the negative 3 moles of H plus that remains. Okay. And so if you guys recall, the pH is equal to the negative log of the concentration of H plus at equilibrium. And so concentration is molarity. And so here, at this point in time, we actually have a discrepancy in units. We cannot plug in this value that we got into pH and into the formula for pH just because we're still in mole units. And so we're going to go ahead and transform this moles into concentration by dividing it by the volume. And so I'll go ahead and put it off to the side. So to get molarity, okay, what we're going to do is we're going to take the remaining value of hydrogen ions, which is 3.0 times 10 to the negative 3 moles. And then we're going to divide this by the total volume. And it needs to be in liters. So there's two items that we have to consider in the denominator. We have to make sure it's the total volume of the solution, and it needs to be in liter units. Okay. So let's think about what just happened here. We have a 50 milliliter. There's so many circles that's going on. Let me just erase some stuff here. All right, so here in this case, we have a 50 milliliter solution inside the Erlenmeyer flask. And remember, this is where we're going to measure the pH. Okay, what is the pH of this Erlenmeyer flask, of the solution inside the Erlenmeyer flask? And so we're going to, the problem asks you to transfer 10 milliliters of sodium hydroxide. And so if we had an initial volume of, if we had an initial volume of 50 milliliters, this is what we're going to add. And so therefore the total volume is 60 milliliters. So we're going to put in 50 milliliters plus 10 milliliters, which is the addition. And that gives us 60.0 milliliters. Okay. And so we need to make sure that this milliliter is in liter. And we're just going to move the decimal place 3 times to the left, okay, giving us 0.0600 liters. And so we're going to take this 3.00 moles, 3.00 times 10 to the negative 3 moles, of H plus that we have remaining, and we're going to divide it by 0.0600 liters, and that's going to give us the pH of our solution. And so the concentration is going to, I'm sorry, it's not going to give us the pH of the solution. It's going to give us the concentration to get us to the pH of the solution. And so the concentration is 5.00 times 10 to the negative 2 molar. And so now that we have the actual concentration, which is 5.00 times 10 to the negative 2 molar, we're going to go ahead and take the negative log of it. And we will see that the resulting pH is going to be 1.301. Okay. And so here we have 3 sig figs, so we have to report 3 places after the decimal. Great. And so it turns out that during our titration, if we add 10 mils of sodium hydroxide, the pH of the analyte after the addition of 10 mils is going to be 1.301. And so if you guys are looking at this pH value and the first pH that we calculated, it didn't increase by very much. Okay? And the reason why was because the amount of base added was not enough to change the pH unit significantly. And so since we are trying to use these pH values to build our titration curve, we're going to go ahead and state that when we added 10 mils of the base, the resulting pH is 1.301. Awesome. So this second step was a little tricky because there was a lot of moving pieces, right? There was a reaction that's occurring, and we needed to determine the equilibrium amount of the hydrogen ions that remains after the reaction occurred. And then we took the moles, the resulting moles at equilibrium, and then we converted into concentration. And then we finally took that concentration and performed the negative log of it to get us the pH of the solution. Okay. So everything that you guys learned in part B of this problem is nothing new. The only thing that's new is putting the pieces together, right? So that's the challenge of this problem. All right. And so I'm going to go ahead and just copy the next problem that we're going to be working with. So the next part to the problem. And I'm also going to copy our picture. So what we're doing is like resetting it, right? We're resetting our image to represent the new part in the problem. All right, so what we're going to do is we're going to calculate the pH of the analyte. And so this is the analyte, so we need to determine the pH, once again, of the solution when the equivalence point is reached. All right. And so let's go ahead and talk about the equivalence point again. If you recall from the previous lecture video, the equivalence point is when the number of moles of acid is equal to the number of moles of base. And so when we reach the equivalence point, we have equal moles of acids and base. So in other words, the number of acid, the amount of acid equals to the amount of the base, such that they neutralize each other. Okay? So imagine like a battlefield of acids and bases. If both sides have equal amounts, then each of them will take each other out and they'll neutralize each other. Long story short, no one is the winner. And so the pH of the solution is going to be 7. Okay, you can quantify this, but this is like the shortcut to answer this problem, conceptually speaking, right? We're at the equivalence point. Okay, and by definition, the number of moles of acid is equal to the number of moles of base. And so remember that we're using these mini problems to determine to determine each point in the titration curve that we're going to sketch later on. And so in the previous problem, notice that I have summarized that if I add 10 mils of the base, it's going to give me a pH of 1.301. And in the previous problem, I've summarized that if I didn't have any base in my solution, the pH, oh, here it is, there's my summary. My pH is going to be 1. Okay. And so to keep with that trend, not only do I need to solve for the pH, but I also need to solve for the volume of the base. Okay. And so what we're going to do is we're going to determine the volume of the base when the pH is neutralized, when the pH is exactly 0. Okay. And what we're going to do is use one of the equations that I've mentioned a little bit earlier. Not in this lecture video, but in the previous lecture video. And so we're going to take a look at this equation. I'll write this bigger. So remember, at the equivalence point, we can use this equation. The molarity of the acid times this by the volume of the acid, divide this by the number of moles of acid, is equal to the molarity of the base times this by the volume of the base, divide this by the molarity of the base. I'm sorry, divide that by the number of moles of base. And so in this scenario, when we're at the equivalence point, we can go ahead and use this equation. And by using this equation, we should be able to determine the volume of the base that we need to add to get us to our equivalence point. And so when you guys were doing this in lab, you guys were like predicting how many drops of titrant you needed to reach your equivalence point or your endpoint, your phenolphthalein to turn a very colorless solution into a very faint pink color. If you guys applied this equation and if you guys knew every single component in this equation, you guys can determine how much volume of titrant that you guys need to put into the solution. And that'll give you a more precise way of determining the endpoint. Anyways, let's go ahead and look at the pieces that we have here. The molarity of the acid is going to be 0.100 molar. The volume of the acid is going to be 50 milliliters. And it's okay for me to just leave volume in milliliters just because we're taking a ratio of two volumes, right? And so we want to express volume at the very end in milliliters anyways, and we're not trying to solve for moles, so we'll just leave it as is. And the molarity of the base is already given to us. It's 0.20 molar. For Na and Nb, that's coming from the reaction that's occurring between these two substances. And so if we have HCl plus NaOH, it's going to produce H2O and our salt. And if you look at this neutralization reaction, and if you balance the chemical equation, you'll find out that it's a 1-to-1 to 1 to 1 ratio. And so it is these coefficients that's going to be placed in the denominator. Okay. And notice it's a 1-to-1 ratio. And so therefore, my equation, if I just clean up, if I clean up my work, will be 0.100 molar times this by 50 milliliters. Divide this by the coefficient of 1, which is this value here, because this is my acid. And in the side of my base, I have 0.200 molar times this by VB over, once again, 1. And that 1 is coming from the coefficient in front of sodium hydroxide. And so to determine the volume of the base, we're just going to go ahead and divide 0.20 to the opposite side. And so I'm going to get 0.10 times this by 50 mils. And I'm going to go ahead and divide this by 0.2. And so the volume of the base is going to be 25 milliliters. Okay. All right. And so the volume of the base using that equation is going to give me 25.0 milliliters. Now, this pH and this volume is going to describe the third point in my titration curve. Okay. All right. So now that we finished part C, we're going to go ahead and perform part D. And once again, I'm going to go ahead and copy this image. Okay. Just to act as a reference point to what I'm doing or what my initial conditions are. Actually, let me take a step back. So now that we calculated VB, which is 25 milliliters, what does that mean in terms of a titration? That means that if we added exactly 25.0 milliliters of sodium hydroxide into my Analyte, my Erlenmeyer flask, what I'm going to get is the endpoint, the equivalence point. And that endpoint or equivalence point, you should see in lab, gives me that nice, beautiful transition in color. If my pH indicator is going to be phenolphthalein, so it's going to go from like colorless to very, very light pink. And so we've now quantified how much volume we actually really need to add from the burette into the titrant to reach the endpoint. All right, so if you look at this volume here, so we're going to once again calculate the pH of this solution. when 50 milliliters of sodium hydroxide is added. And so if you look at what the volume that we added here, we added 25 milliliters, and 25 milliliters will give us the end point, will get us to the end point. And so since 50 milliliters is past the end point, what that means is that we're going to have an excess of titrant. And since the titrant in this scenario was a base, we're going to have an excess of the base. And when we have an excess of a base, the pH should be high. Okay, so this is the last point in our titration curve that's going to be found closer to the top of the graph. It's going to be that represents, the y-axis represents the pH, the increase in pH. Okay. You guys will see this in just a second. All right, so let's go ahead and think about what's happening here. So we have sodium hydroxide reacting with hydrochloric acid. So here we have, and I'm going to represent HCl as just H+, because I know that my Cl- is a spectator ion. Same thing with sodium. So I'm going to represent NaOH as just OH-. And so I'm going to have H+, this acid, reacting with hydroxide, and it's going to go ahead and combine to produce water. Okay. So this is my overall chemical reaction that I'm working with. And once again, my water is going to be liquid in state. Okay. Now, since a reaction is occurring, and since I want to figure out my pH, that means that I need to figure out the concentration of my H+ at equilibrium. And since a reaction is occurring, then that means that we need to describe the key points in the course of the reaction using an ice table. So we want to know the initial amounts, we want to know the change, and we want to know the equilibrium values. And whenever you guys are describing this reaction, you want to do it in mole units. Okay. And we can always convert the mole units into molarity at the very, very end. And now if you want to use molarity in terms of your initial, then you guys can do so, but you'll have to perform that, you'll have to recalculate the concentration at the very, very beginning instead of the very end. All right, and so looking at my acid, I have 0.1 molar hydrochloric acid to that of in 50 milliliters. And so to calculate moles of H+, I'm going to convert 50 milliliters into liters. So that's going to be 0.0500 liters. And you don't want to drop these zeros because they're significant. They act as significant figures. And we need to make sure our sigfig count is consistent all the way through. And then we're going to go ahead and take that 0.0500 liters and we're going to multiply it by the concentration. And if I recall correctly, it's going to be 0.100. So it's going to be 0.100 moles for every 1 liter. And that's the definition of molarity. Oops. That cancels out. And if you multiply those two, so 0.05 times that by 0.1, that's going to give us 5.00 times 10 to the negative 3. Moles of H plus. Okay, so that's what we're going to put here. 5.00 times 10 to the negative 3 moles. All right, and so we need to determine how many moles of hydroxide we're actually putting inside this Erlenmeyer flask. And that's going to be dictated by the concentration and the volume that we're using. And so here in this case, for moles of OH minus, or our base, it's going to be the 50 mils. Oops. Okay. So we have 50 mils. That's going to be converted into 0.0500 liters. And then we're going to take this 0.0500 liter of hydroxide, and we're going to multiply it by the concentration, which in this case is going to be 1 over 0.200 moles. Okay. And so when we multiply both of them, 0.05 times that by 0.2, that's going to get us 1.0 times 10 to the negative 2 moles. Oh, what happened? Of hydroxide. Then we're going to go ahead and take that value, oh geez, and we're going to place it here. So we have 1.00 times 10 to the negative 2 moles. All right, once again, we have this battlefield going on where the acid is battling it out with the hydroxide and vice versa. And so which do you think will dominate? Which one will lose, so to speak? Okay. And so it turns out that in this scenario, in this case, this negative 3 is going to be much smaller than a negative 2. And so therefore, the acid lost in this round. There's just too few of those substances to neutralize hydroxide. And so it is hydroxide that's going to dominate in this round. And so therefore, we're going to subtract 5.00 times 10 to the negative 3 moles. And it's going to be minus 0.500 times 10 to the negative 3 moles. Okay. So at equilibrium, we'll have no more acid. Okay. However, we still have 5.00 times 10 to the negative 3 moles of the base. So if you add downward, you get 5.00 times 10 to the negative 3 moles of the base. Okay. And yes, we'll add this number of water, but once again, we don't really care about water because it really it's not going to determine the pH of my solution. Okay. And so looking at what we have here at equilibrium, in this case, we have hydroxide. We don't have hydrogen ion. And so to calculate the pH, we need to do some other stuff. So pH is equal to negative log of the concentration of H plus. Okay. So you guys can either convert, hydroxide into concentration of H plus, or you guys can calculate the pOH and then take that from 14 to determine the pH. Okay. But before you can do any of that stuff, I want you guys to notice that we have this bracket, and once again, this bracket represents molarity. And so what we're going to do is calculate the molarity of hydroxide. What is the concentration of the hydroxide? And we already have the first part to it, which is 5.00 times 10 to the negative 3 moles. And all we have to do is divide it by the total volume. Okay. And so it's very important for us to consistently write our units over and over and over again, just to remind us what we have. And so here, the total volume is representative of the sum of how much we added and how much we initially had. In this case, it's 50 plus 50, which is 100 mils. And so if I wanted to express that in liters, which I should because I'm calculating molarity, that's going to be 0.1 liter. And so I'm going to divide this number of moles by 0.1, and then that's going to give me a molar concentration of 5.00 times 10 to the negative 2 of hydroxide. Okay. And so once again, you guys can do one of two ways. You guys can convert hydroxide into hydrogen ion by using Kw, or you guys can take this hydroxide and then calculate the pOH and then convert into pH. So either path will get you to the right answer. I'm just going to go ahead and choose this path just because I can press negative log very quickly into my calculator. So negative log of my answer, it's going to give me a pOH of 1.301. So please be careful. This is not the pH of the solution. This is the pOH. And so if I take 14 minus 1.301, I'll get my pH. Okay, so 14 minus the answer is going to give me 12.699, and I'm rounding it to the correct number of sig figs, so 12.699, and that is the pH of my solution when the volume of the base that I've added is 50.0 milliliters. Cool. So we did it. We calculated the pH of the solution when we added 50 milliliters of my base. Okay. And so hopefully you guys understand my logic, my train of thought in terms of calculating each part, each component for part D. And it's nothing, once again, these calculations are nothing new. You guys know how to take the pH. You guys know how to write an ice table. You guys know how to calculate the moles for molarity. But now we're just going to put it in, like a different type of setting, different type of word problem. All right. So let's go ahead and look at part E. Part E is asking us, sketch the titration curve. All right, and so to sketch our titration curve, we're going to have to summarize all of the key points, all of the answers from parts A through D. So remember, the titration curve the axis is pH against volume of titrant that was added. And the titrant that was added in this example is a base. So it's VB. And this should be expressed in milliliters. Okay. So I'm going to go through my notes, and I'm just going to copy and paste all of my answers, the ones that I boxed. Okay. And so for part A, maybe I'll just do it on the side here. So for part A, remember that we had 0 mils of volume of the base. Remember we're calculating the initial pH, and the initial pH was 1. I think there was another 0. I can't remember. And so for part B, we added 10 mils of the base of the titrant, and that gave us a pH of 1.301. Now for part C, we added 25.0 mils of the base. Okay? And remember, this 25 mils gave us our endpoint. Equal number of moles of acid, equal number of moles of base. And so the pH is going to equal to 7.00. Part D, which is the one that we just finished, 50.0 milliliters of the base, and the pH went to 12 point, that one I can't remember, 699. Okay. So we're going to use all 4 of these points to graph, to sketch our titration curve. And so the first thing I'm going to do is I'm going to label my y-axis. So I'll just roughly say this is 1, 2, 3, 4, 5. I think I'll have enough. Okay, I'll give it more room. So I'll just do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, maybe not enough room. So I'll zoom out. Okay. And I'm going to scoot this down. Power of technology. All right, and so this is going to be 11, 12, 13, 14. And so the reason why I'm stopping at 14 is because my pH range is typically from 0 to 14, right? And so the volume of the titrant, this one I can go ahead and estimate. So notice that I have a range of 0 to 50. So I just want to make sure I give enough to not squish my points in one area. And so this is going to be 0. So I need 50. So I can probably do it by 5s or 10s. Let's do it by 5. So 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. That's pretty good. All right. And so this is all in milliliters. All right. So now that I've made my graph, I'm going to go ahead and start sketching. And so at 0 milliliters, I have a pH of 1. So I'm going to represent this by, let's do purple. So it's 0 milliliters, my pH is 1. Okay. So that's my first point. So hopefully you guys see that. My second point, it's going to be 10 mils, and that's going to be 1.301. So here's my 10 mils, and then 1.301 is just slightly above my first point. Okay. And so it is a huge estimate. That's okay. We're not being precise right now. We're just sketching the titration curve. So the next one will be 25 mils, and that's 7. And so I'm going to go ahead and just, I think the best way for me is to use this feature. Okay. And so it's right here. Let me clean up. Okay, that's pretty good. Okay. So this is my endpoint right here. Last but not least, I have 50 mils, and it's 12.699. So here's 50. Let's see if I can sketch up. And so if you guys are doing this on your own, please use a ruler. And so 12.699, so that's just somewhere above, slightly above. And it's a sketch. I'm not gonna fight it. So let me just go ahead and put this in pink. Okay. Then I'm gonna erase these two. All right. So we have all 4 points that we calculated. And to sketch our titration curve, what we're going to do is we're going to sketch this way. So there isn't a more exact method, but I guess since we're just sketching, we're gonna. So right when we approach, or as we approach the endpoint, what we're going to do is we're going to start curving our titration curve so that it is vertical. We have this steep curve right at 25. And then as we pass that 25, we're just going to go ahead and start sketching, and we're going to kind of curve it to hit that last point. Okay. And so this is point A. So that's the point from part A of the problem, part B, part C, and part D. All right. And so we sketched our titration curve. Just remember that when you're sketching these titration curves, if you want to put a line passing the endpoint, so that way, just to kind of let you know that as you approach this vertical line, you want to start curving your titration curve, and as you pass that vertical line, you want to curve it once again. There is a much more precise method of doing it, but it's out of the scope for this class for now. I guess another way would be to take the slope, right? So draw a line between those 2 points, but that would require you to have 2 points for part D. Okay. And so where those 2 lines kind of meet, you're going to kind of curve downwards or upwards, depending on how you're curving it. And then you can just go ahead and erase those lines. Right? But that would require that you have more points on this graph than what we currently have right now. And so we did it. We drew our first titration curve. And so this is the titration curve that describes your strong base, which is your titrant, being added to your strong acid. Okay. So this is a very characteristic titration curve for a strong base to a strong acid. The strong acid is going to be our analyte. Okay. All right, so in the next video, we are going to reverse the situation. We're going to treat our strong acid as our titrant and our strong base as our analyte. And we're going to see what that titration curve looks like. All right, catch you guys later. Bye.